11th module is by Dr. Cenko. He's the principal investigator of the Neil Gerald Swift Observatory. So he is an expert on all things gamma ray, X-ray. Well, I guess you have to work with every single piece of the spectrum. Okay, he's an expert on the electromagnetic spectrum.
Thank you, Monsi. Thanks, everyone. It's nice to be here. It's been really fun to see what an engaged and sort of interactive people you are. So I hope, throughout this, I hope you can continue that. If you have questions, feel free to raise your hand. And, you should not be to me the whole time, or everyone. So for the last two lectures, we're going to kind of shift. A lot of the emphasis up to this point has been on the optical bandpass. And so from here, you're going to hear from me about higher energies. X-rays is maybe pushing up into gamma rays a little bit. And then after this, David Kaplan will tell you more about radio wavelengths. So first of all, so we're all on kind of the same footing. What are we talking about when we're talking about the X-ray bandpass? This is a plot of, if you imagine you have a source that it's emitting equally across all wavelengths, but it's located at some distance away from you. And there's some neutral hydrogen and other material in the interstellar medium between that source and you. That material is going to absorb photons of certain wavelengths. And in particular, if there's neutral hydrogen, because it has atomic transition at 13.6 electron volts, you'll see a really sharp drop-off in the flux at this wavelength, 13.6 electron volts. This is kind of what defines the extreme ultraviolet range. So ultraviolet wavelengths extend down here down to about 10 electron volts. This sort of gap here is where it's very hard to observe across the spectrum because of this interstellar absorption. It's called ultraviolet. There's very little astronomy that kind of happens at these wavelengths. And then the X-rays pick up somewhere around 0.1 keV. An electron volt is the amount of energy you get taking one electron, accelerating it across a potential of 1 volt. And this is kind of what defines, roughly speaking, the start of the X-ray bandpass. So 100 eV, 0.1 keV, that's roughly where we're talking about X-rays. And then at the high end, it's not so much physically motivated. Push up maybe to around 100 keV. Depends on who you talk to exactly where that will be. But that's what we're going to call the sort of X-ray bandpass. Again, below that, we're looking at extreme ultraviolet and far ultraviolet. Above that, we're pushing into the gamma rays, which runs over many orders of magnitude in wavelengths. A little bit extra terminology here. People talk about soft X-rays or hard X-rays. So soft is another way of saying lower energy X-rays. The exact cutoff, not extremely well defined, but energy is less than 1, maybe 2 keV, where you start to see really, pretty strong absorption, generally from this interstellar material. Harder X-ray, above few, maybe above 10 keV. This is where you're not really seeing much attenuation from what's ever along your line of sight. So if I say soft X-rays, think maybe 1 keV. If I say hard X-rays, think 10 keV or above. Why do we actually care about this bandpass? I'll take the words of our fearless leader spoken on the first day here. If you want to be a budding time domain astronomer, you have to be wavelength agnostic. If you look at the entire electromagnetic spectrum, our eyes are actually sensitive only to a very narrow range, right? And it's not a surprise that range is where most stars in the sky, and particularly the sun, emit the bulk of their energy. But there are many physical processes going on in which you're not going to see sort of the bulk of that energy coming out at these wavelengths. In particular, X-rays are useful for two classes of sources. The first of those are sources that are emitting thermally, but instead of at temperatures of a few thousand Kelvin, like most stars, at temperatures of 1,000,000 Kelvin, maybe even 10 million Kelvin. So if you take a black body spectrum, this is a black body spectrum of a source that's sitting at quite hot, so it's actually peaking in the UV at 32,000 Kelvin. This is from study, if you remember the transient AT 2018 COW, or the COW as it was known. Maybe you heard this sort of very strange nomenclature. Had a very complicated spectral energy distribution. But if you look at something, that's peaking in the optical UV, you'll see this relatively narrow thermal distribution. You drive that temperature up, the peak of the spectrum will push out into X-ray wavelengths, 10 to the 17, 10 to the 18 hertz. It's equivalent to the kind of 10 keV that we were talking about before. So that's one class of sources in which X-rays are very useful for, things that are extremely hot, very hot plasmas. But the other that's actually probably much more relevant for transient time-domain astronomy is for sources that are non-thermal, where you can accelerate electrons at high speeds, you can get synchrotron emission, inverse Compton emission, a variety of other non-thermal processes, and so you're not limited to this relatively narrow range of frequencies over which most of the energy is coming out. And instead, you can see power laws extending over sort of a vast range of the electromagnetic spectrum. So usually when we're talking about what kind of emission processes are happening in the X-ray and transient world, we're talking about non-thermal processes, and as a result, sort of the nice thing about having the radio talk immediately following this is that usually sources emitting X-rays are also emitting radio emission. This non-thermal radiation across many orders of magnitude in wavelength in the electromagnetic spectrum. The next thing to know if you want to study X-rays is that you are by default limited to looking from high altitudes. Okay? The atmosphere is extremely effective at absorbing X-ray wavelengths. This is very good for us. In particular, our DNA is quite sensitive to hard X-ray energies, and so would be damaged if we were actually exposed to this in large amounts. Great for us in terms of being able to survive. Bad for us if we want to study sources that are emitting cosmic X-rays. So a plot of the atmospheric opacity is a function of wavelength. You can see basically anything above kind of the sort of near ultraviolet wavelengths. We can see this is the sort of far, blue end of the rainbow here. Very effectively absorbed by the atmosphere. And so if you want to look at X-rays, if you want to look at far ultraviolet, if you want to look at gamma rays, you have to go above the atmosphere, above a few hundred kilometers. You could do that with sounding rockets. That's one way to do it. And so the first experiments that were able to detect cosmic X-rays from things like the sun and SCO X1, actually aboard sounding rockets where they only flew or above this altitude for a short period of time. You do it now with high altitude balloons. They're able to get there, and instead of experiment lengths of order a few hours, you can get experiments that last for up to a few months in some cases. If you really want something that's up there that's going to be taking observations for a long period of time, you need to go into space and put a satellite in orbit of some kind. And so X-ray astronomy is inherently space astronomy. This is one of the reasons why people at NASA. You'll see a large concentration of high-energy astronomers, X-ray and gamma ray people at a place like NASA, because if you want to go to space. Okay, the next sort of critical piece, if you want to understand the data product and the analysis that are coming to that, is that X-ray telescopes are inherently very unlike optical telescopes. And the reason for this is because X-ray photons are so energetic that almost any material that you put at the end of them, if you send an X-ray in at a normal incidence, like most optical telescopes will be sitting at, will be completely absorbed. You don't get reflection, or you don't get, sort of bending of light like you do in lenses from X-rays. They're just too energetic. And so you have two choices to deal with this issue. There are sort of two broad classes of X-ray telescopes that are out there. The earliest systems, and still there are a large number of them in place, are some kind of what we would call a coated aperture mask. So what you do here is out at this plane up here, this sort of optical plane, you populate the area with material like lead that actually is capable of absorbing high-energy photons. But you do so in some kind of pattern. You create a mask, okay? So that photons that come through and hit one of these tiles will be absorbed. Photons that miss one of those tiles will go through and hit your detector. And then depending on where the source is located on the sky, it'll create a distinct shadow pattern on your detector. So you can do localization, a differentiation between different sources by creating the shadow pattern on your detector. So this is nice. It's very, you can get large effective areas doing this, right? There's nothing that's blocking or reflecting the X-rays getting your detector. You can sort of very efficiently get effective collecting area using this technique. The challenges are that, it's not generally easy to get high sensitivities. Because if you want to look over any reasonable area on the sky, you have to have a really big detector, physically large, sort of actual size of the detector. So you're accepting background from all the areas that are not from your source, right? If your source is this one, you're looking here, you're getting photons here, but you're also getting other photons that are coming in through here, other photons that are coming in through here. You're not getting the benefit of focused light that you get from an optical telescope. So this is one of the downsides of a coated aperture mask. So it is possible to focus X-rays, but in order to do so, instead of at some kind of normal incidence, you have to do it at very shallow or grazing incidence angles. And typically by very shallow, I mean an angle 10 or of order 1 degree. Okay? So the sort of standard design for this is called a Wolter 1 telescope. There are also Wolter 2 and Wolter 3, although I don't remember what they are. But you have paraboloid mirror segments and hyperboloid mirror segments. Double reflection on both of these. Focus X-rays to a point down here. So this allows you to achieve much larger sensitivities in the same way that focusing optical telescopes allow us to do that, which is great. You can get really tremendous angular resolution doing this, comparable to actually what ground-based optical telescopes are able to achieve. Unlike here, for aperture masks, where the angular resolution on the sky is quite poor. But the challenge with this is it's really not the most efficient way. You have to fly a lot of mass in order to get any kind of reasonable effective area up there on the sky, right? Because each of these is a mirror segment, but you're only sort of grazing off of this mirror segment, and you need a lot of area in order to do that, but only a small amount of area is actually up there on the sky. So when we're thinking about space instruments, something we always have to keep in mind is we have a limited amount of mass that we can actually launch on any kind of payload. And so we're relatively limited in the amount of effective area that we can have on the sky. For example, one of the largest effective area X-ray telescopes that's currently operating at the moment, the Chandra X-ray Observatory, has a total effective area at 1 keV of order 400 or 500 centimeters squared. If you just convert that into, what kind of effective area an optical telescope would be like a 10 centimeter telescope. So the largest, X-ray telescope, $1 billion X-ray telescope that we have operating has the effective collecting area of 10 or 12 centimeter optical telescope. And it's because you have to do this sort of very complicated procedure here. Okay, so I think I went through most of this. Coated mask telescopes. I'm not going to talk about this too much in the lecture because we're going to go through data analysis from a couple of coated mask telescopes. And we do sort of hands-on set at the end. Inherently large field of view. You can get very high energy photons with this, large collecting area, but very high background and poor spatial resolution. So the burst alert telescope, this is an image of this. It's actually this sort of plane that's almost 2 meters across with a large number, I can't remember, several tens of thousands of very small lead tiles in this very irregular pattern sitting here that can image large areas of the sky at hard X-ray wavelengths. X-ray timing explorer, several of the instruments on the AstroSat satellite. Sort of a very common and well-honed technique to cover large areas on the sky, to do it at high time resolution, but not with extreme sensitivities. And the focusing telescopes, you get excellent spatial resolution, low background, higher sensitivity, but low ratio of effective area to mass. And the other downside is you need relatively long focal length, right? You need grazing incidence angles, so the distance between where you place your detector and where you place your mirror needs to be pretty long in order to do that. And again, if you're launching something into space, you have a relatively confined volume in which you can put it in if you want to get up there. So that either limits the focal length to something like of order 10 meters, which is what Chandra uses, Or if you want to be creative, you actually have to have some kind of mechanism, like NuStar uses, to physically separate your optics from your detector after you launch. Kind of like deployable system. The way that most of these telescopes work is that instead of using just kind of single optics, they use nested groups of optics, so that you're sampling slightly, increasing range of angles from out here. And this way you can increase your, collecting area significantly. But again, it's quite limited compared to what you can do in the optical. The detectors that are sitting at the end of these telescopes, in particular for things that are focusing telescopes like Chandra or XMM, are almost always charge-coupled devices. So these are the same devices that you see, we heard about in optical astronomy lecture. They operate similar to the way that optical CCDs do, but with a few kind of important differences, things that we want to keep in mind when we're starting to get into data analysis stuff. They typically have much faster readout times. Okay? Instead of actually for a fixed amount of time, opening the shutter for that time, collecting light for that amount of time, and then reading out. These are almost always operating at much faster readout time of order seconds, sometimes much faster than that. And so instead of a data product being an image, the data product that you get out of one of these detectors is a list of photons called an event list. Okay? And each of those photons is tagged with pixel coordinates, an X and Y. It's tagged with a time at which it arrived. And X-ray CCDs are actually capable of providing relatively crude, but better than optical CCDs, energy resolution. It's the energy of the incident photon to something like 5 or 10%. Okay, so all right, this was a photon that hit at this time, this pixel X and Y. It has an energy of about, 0.5 keV, or about 2 keV. And the sort of data product it is just a long list and a fits table of all of these events. You will see, almost certainly, if you continue in this field in the relatively near future, microcalorimeters. These are a very different detector technology that are capable of providing significantly better energy resolution. If you want to do X-ray spectroscopy right now, the way that it's done with something like Chandra, better than the resolution that you get with a CCD, you actually have to employ something like a grating, the same way that an optical spectrograph is going to work. But they're not very efficient. They just the light over a large number of pixels, and so you can only do any kind of moderate resolution X-ray spectroscopy with very bright sources. Microcalorimeters are capable of producing very high energy resolution without actually adding this extra dispersive element along the path. And so you can look at much fainter sources to much higher resolution. If you've ever heard of the Hitomi mission, this is one of the first one of these operate technology in space. It delivered some really amazing observations of galaxy clusters and supernova remnants, but unfortunately the satellite had some issues sort of launched and then ended up breaking. And so there are future collaborations that will be flying this, hopefully, for more extended periods of time in the next sort of 3 to 5 years. Okay, again, so the data products that we're getting out of these detectors, event lists, you get position, time, and energy. You can do a variety of things with these. You can take all of this and make an image. You can take the number of photons as a function of time and make a light curve. Take the number of photons as a function of energy and make a spectrum. In practice, what we usually talk, the sort of words that we use is how do we process some of this data. So we're going to apply some filters to it. Usually we're only interested in, let's say, one particular source. And so we'll filter based on position of the detector. Or we're only interested in some energy band, and then we'll limit the sort of the energy range. So we'll apply a filter based on that on our event list. Much like optical, the majority of X-ray facilities are going to return data to you in a FITS file. If you worked with FITS files earlier, that's good. Sort of be very familiar with this. contain a number of extensions, sometimes images. Usually these event lists will be in tables. And the one other kind of piece that we have to keep in mind here, in addition to this events table, is in X-ray astronomy we very frequently deal with something called the good time interval. X-ray observatories are up in space, and the dominant source of sound is coming from a variety of different things. But the background that you see at X-ray wavelengths is, number one, low, much lower than you'll see in optical astronomy. That's good. We like low backgrounds. But number two, it's significantly more variable. What you see is large flares of soft protons coming in from the sun discharging energy. If you have a satellite in a low Earth orbit, you'll pass through a period regions of the Earth's atmosphere that have much larger particle fluxes. For example, the South Atlantic anomaly, or the poles, the North and South Pole, where the magnetic fields that are surrounding the Earth sort of come together. You get large charged particle fluxes. So if you look at the background rate from a typical XMM observation, you can see that for the most part it's pretty steady, but that there are these regions of relatively short-lived spikes or flares. Okay, and we want to filter those out, and the count increases here, right? Up from something like 50 to something like 1,000 on a very short time scale. So we want to filter those out if we're looking at our data set. The other thing that we want to keep in mind is that if we have a satellite that's in a low Earth orbit, something like SWIFT, like Astronomy, for example, it's orbiting the Earth every 90 minutes. And so it's only capable of seeing any spot on the sky for something like half of that time. The other half of that time, that spot will be blocked by the Earth. So if you want long observations of any spot and you're staring at one spot, you have to account for the fact that you're only seeing Earth's field of interest for some fraction of an orbit. And that's also accounted for in these good time interval files that will come with the data sets that you get. So the great thing that I like about X-ray data analysis, in particular from imaging detectors like Chandra and XMM, is that if you can count and you can take square roots, you are capable of doing X-ray analysis. That's really all that you need. As I said, the background rate is really low. Typically, frankly, the source rate is quite low as well. I'll show some examples of this in just a second. And so rather than being in a Gaussian regime like we usually are, and we're looking at optical images where we're largely background dominated, almost all of X-ray astronomy is in the sort of regime, in the low number statistics. So if you're in the Poisson regime, you have some expected number of count rate, this mean, and you want to know what's the probability of seeing some other number of counts, some exposure time. It's given by the Poisson probability distribution. So here are a few examples of this. If your mean is 1, say you take a 100-second exposure, and you expect in that 100-second exposure that you should see 1 photon. What is the probability of seeing a number of different photons? You have a high probability of seeing 0 or 1, and then it falls off quite quickly as you go to higher energies, specified by this probability distribution. Same thing for 4. Again, if you're expecting 4 photons in that exposure time, not surprisingly, it peaks around 4 or 5, but it only peaks something like 20% of the total probability. There's a sizable probability that you'll see a smaller number than that or a larger number than that, and it gets broader as you go to sort of higher mean numbers. If you drive this up to really, really large numbers, it starts to look Gaussian. But at the low numbers we're typically dealing with, it's really sort of a Poisson process. What does that mean? What that means is that, again, sort of another sort of just set of numbers. If you're expecting, sort of 12.5, there's some broad probability range. The probability of seeing 12 or 13 is only relatively modest. And each observation is just kind of a random sampling of this reality is one way to think about doing the analysis associated with this. The other thing, the reason why I said if you can count and do square roots and you can do X-ray imaging analysis is because the standard deviation of a Poisson distribution is just the square root of the mean, which is roughly what's corresponding to our uncertainty on any given measurement that we make. And so for small numbers, this is really going to dominate our signal-to-noise ratio. If we're expecting, let's say, 10 counts in some exposure, the fractional uncertainty in this, the square root of 10 over 10 is about 33%. So that's roughly like a 3 sigma, detection. If you're able to increase this by an order of magnitude, it's only driving up the signal-to-noise ratio by, a factor of 3 or so. Okay. So for higher number of photons, if you get high enough number of photons, the statistical noise is going to be a smaller fraction. Kind of that in more mathematical form. What we want to do is, if we imagine we have sort of incoming individual photons from the source with a count rate S. So this is the source that we're trying to study, just some number of photons per second. And there's some background rate, which is B photons per second. An exposure of time t, the total number of photons we're going to see is going to be the sum of the source plus the background. And the uncertainty on that is just going to be the square root of that number. If we assume uncertainty on the background, just subtract off the background rate, and then the number of our source is going to be source times time, and this is going to be giving us our uncertainty. So what does this actually look like in practice? Okay, so here's an actual image from Chandra. This is a 10 millisecond exposure taken on a ZTF source from 6 months ago. I honestly have no idea which one. A couple of things to note. So again, right, Chandra is $1 billion class observatory, one of the largest effective area telescopes that we have that's operating at X-ray wavelengths. And in this 10 kilosecond, so roughly 3-hour exposure, the vast majority of pixels here have 0 counts on them. Okay, the X-ray sky is just really quiet compared to what it used to at optical wavelengths. The way that most of this analysis is done, if this is where our source is, same way we saw when we were doing optical aperture photometry, define some region where we sum up the number of counts in this source, our source region, define some annulus that we're going to call our background that ideally is source-free. Based on this, calculates what the estimated background rate should be in our source region and subtract. Just looking at these numbers, here's an example for a 10 kilosecond exposure time. In that data, there were 11 source counts in our region of interest. The expected number of counts from the background region was only 1.3. And so our count rate, when we subtract these two, is 9.7 by 10 to the minus 4 counts per second. The uncertainty on that is going to be just dictated by this sort of square root of 11 divided by the exposure time. So if you look at this image, it doesn't really look like much. The signal-to-noise ratio, and this is, again, something that's relatively peculiar to X-ray astronomy. Signal-to-noise ratio of this image, because you're completely dominated by the uncertainty in the number of counts in your source, is actually relatively modest, less than sigma, we would say. But the significance of the detection being, how many counts do you see compared to how many counts would you expect if you were just seeing from the background, is quite high. So you know that something's there, but you just don't really know how bright it is. It's a relatively common place to be in the X-ray astronomy world. Okay? Does that all make sense? Good. Okay. So once you have a count rate measurement, the sort of standard, unlike the optical world or the radio world, where you're telling you things in magnitude, Jansky, millijansky, microjansky, Jansky, whatever you want. X-ray measurements are usually actually reported in useful flux units. maybe more than useful, kind of like I'd say intuitive flux units. So we report something like the ergs per centimeter per squared over some bandpass. Typically, 0.3 to 7 keV, 0.3 keV. For most imaging X-ray telescopes, this is where most of your sensitivity is setting. So to convert from this measured count rate, in order to get to information on what the flux of the source is, we actually have to know something about the spectrum. Because unlike the optical, where we have a filter looking over a relatively narrow range in wavelengths, X-ray bandpass, we're looking from, 0.2, 0.1 keV up to 8 or 10 keV. This is several orders of magnitude in wavelength space. And so a source that has a spectrum that looks like this versus a source that has a spectrum that looks like that will have pretty different conversions to get from count rates to fluxes. The challenge here is that low count rates, as I said before, for this source we have 11 counts. Okay? You will see people make X-ray spectra with 11 counts. It's calling it a spectrum is a little exaggeration since each of those is going to have one count in it. But you really can't constrain the spectrum in any meaningful way if you have such few sort of observations to work with. So if you have low count rates, oftentimes you'll assume some kind of spectrum. Okay, and you'll say, well, typically sources of this class show power loss spectra with a photon index. Or we think this source, based on other observations, should be a black body with a temperature of order 100 eV or 200 eV. If you actually have enough counts, where enough is somewhat subjective, but at least a few hundred, pushing into maybe a few thousand, you can model the spectrum. Every photon we get from this X-ray detector has an associated energy with it. So then we know what the response, which I'll get to in a second, looks like. We can model what the spectrum looks like and use that to get a flux estimate. But at low count rates, we kind of just have to assume something about what the spectrum looks like. And the additional pieces of information that we need to do that, if you talk to an X-ray astronomer, you hear a lot about response matrices. What does your response matrix look like? How does it evolve over time? How does it depend on what position of detector, things like that. These are just really two different pieces of information, okay? These response matrices. One is called the RMF, or redistribution matrix file, which is just a mapping between, the detector doesn't actually read out the energy itself. It reads out what's called times a channel. Different, PA is a name for this as well. And there needs to be some kind of mapping between the channel number that the X-ray detector gives you and the actual incident energy of the photon. This is typically reasonably linear, not perfectly. So you can see this is showing you with a linear scale. Typically, channel is pretty well correlated with incident photon energy, but if you blow it up, there are, it's not a perfect one-to-one relation. You have a photon with some channel that your detector is telling you. This kind of information, you can infer what the actual energy of that photon is with some kind of probability associated with it. And the other piece of information that you need is what's a response file, or an ARF. RMF and an ARF. I don't know who comes up with the names for these things. Now, this is what's telling you how much effective area your full system has as a function of energy. Right, and so this is what's shown for Chandra, the numbers I was giving you kind of before. You can see that it's peaking at around a few hundred centimeters per second. The energy is between, let's say, keV, then falls off pretty rapidly at high energies and pretty rapidly at low energies. So if you know what the spectrum looks like from the information that we had back here, and we can pull that through the response file, and use that to calculate a flux from our count rate with all the uncertainties kind of folded through. Okay? So there are a variety of pretty standard software packages to do this. For whatever reason, every sort of laboratory that has flown has kind of their own package tailored to the data that comes from all of it. So if you use Chandra, you may hear people talk about Chow. If you hear XMM, you may hear people talk about SAS. F tools are just kind of general FITS tools that the high energy community uses, released by the HESARC at Goddard. XSpec for doing spectral fitting. I didn't want to delve into any of this, make all of you install any of these on your laptops, because it's honestly getting the installation on is the hardest part and the most time consuming. And once you've done that, usually the packages work reasonably well. But if you have Chandra data, there will be software available, and there are guides online, and they have tutorials, and they have summer schools and all of that. It will teach you sort of every sort of in and out you might want to know about how to reduce Chandra, XMS, Swift data, any of these things. So this is just a list if you want to know where to go to find some more information. So I think what I want to do is finish there for the lecture part and see if anyone had any questions. And then if not, we can dive into sort of the hands-on. We're going to do less with the imaging, focusing instruments, and more with the coded mask stuff.